Hello there. I intend to provide a series of lectures concerning the design of linear power supplies or conventional power supplies. My first lecture will be on the half-wave rectifier power supply. The one you see here in the schematic, where you have the main supplies in here, it's 240 volts or 120. You have your fuse on the primary side. You have your transformer, and I intend to use this transformer for all the types of power supplies. That would give you an idea how to make a good comparison between the various types. And you have that diode or two diodes or bridge rectifier. You have that storage cap, and you have your load. Now, how does this circuit operate? You have the primary side in here, you have the secondary side in here, and you have your center tab. At that center tab is just a piece of wire through the middle of the two secondaries that you see in here. Okay. Now, when you have the signs, the polarities, the blue polarities, that's what we are going to talk about first. You have your positive at this side, you have your negative at this side. And you will have at the secondary the same thing, the positive in this side and the negative in this side. And that's because we have these two little dots in here that indicates that our polarities are the same on these two terminals. You have to note that in all transformers, this is an isolated transformer, the secondary is magnetically coupled to the primary. Therefore, even though this side is referenced to the neutral, and neutral somehow is referenced also to the earth, this side will be floating. So you can practically reference it to anywhere you want in the system. Okay, going back to the function of the circuit, like we said before, when we have a positive here, a negative in here, and that's explained here in the half sine wave that you see in here. Okay, this diode will be forward biased because its anode has a positive and its cathode has a negative. Therefore, it will conduct and a current will flow through the load resistance. At the start, we are not going to consider the cap. The storage element will not be considered. We'll analyze the circuit without the presence of the storage cap. Okay, so this is the half of the sine wave that will be present across the load. Now, when the polarity is reversed, where you have your negative in here, that's green polarities, you have a negative in here, and you have your positive in here. The same thing happens in the secondary. You have your negative in here and your positive in here, and the negative in the cathode, and the anode, means this diode will not be forward biased and it will not conduct. Therefore, the diode will block that part of the sine wave. Okay, this of course will cause harmonics in the system. That's why sometimes this type of of power supply is not used. Okay. Now let's go forward and see the symbols definitions that we intend to use throughout the lectures. This lecture and the series of lectures that are coming. You have that IM, which is the maximum peak current. You have that VM, which is the maximum peak voltage. You have that IDC, it equals the average load current. You have the VDC, it's the average load voltage. You have the VAC, the rated secondary voltage. That's an RMS, and that's what's written in the transformer. You have the IAC, the rated secondary current. It's an RMS value, and what's written in the transformer. You have the PT, the transformer power, which is the VAC multiplied by the IAC. It's in volt ampere. It's not in watt. Okay, that's what's written in the transformer too, or part of the specifications of the transformer. You have that PL, it's the load power, it's in watts. You have the VL in RMS, it's the effective load voltage. You have the IL in RMS, it's the effective load current. You have the IT in RMS, it's the effective transformer secondary current. Now to the equations. The VDC across the load would equal to integrating that half sine wave. You get the function of the sine wave and you integrate it over the half of the sine wave, which is t over 2 to 0. And after finding that area under the curve of the half sine wave, you simply just average it over t. And that would give us a Vm over pi. So whatever that area is, when you divide it, you just divide the Vm, the maximum peak voltage, divided by pi, and that would give you the average DC voltage, which also equals the root of square of 2 VAC, that's the maximum peak voltage, divided by pi. Okay. That comes up to about 0.318 of Vm. So whatever you have, the maximum voltage, that divided by pi, and you get that average VDC across the load. Like we said before, that's without considering the cap, the storage element. IDC, so the same thing, would equal to about 0.318 of Im. Same thing, it's a half sine wave. Okay. The IAC would equal, that's what's written with a transformer. Okay. How you get the RMS of any given shape for a half sine wave? You get that function, you square it, and after that you find the area underneath it, and you average it over the whole of t. Okay. And you root square it, and that gives you an Im over 2. Now what is the significance of that? That tells you that I peak max can be twice as much as the IAC. So what you can have twice as much as what's written on the transformer, okay, without exceeding its specifications. Because the RMS of such a wave, okay, would be equal to Im over 2. And the IDC, therefore, would be equal to about 0.64 of the IAC. Now we'll have our first example. And like I said before, the same transformer will be used in all the configurations. That's the half wave bridge rectifier, that's the half wave rectifier power supply, and you have the full wave center tapped power supply and the full wave bridge. In order to make a fair comparison between all of these types, we have to use the same transformer with the same specifications. The transformer that we intend to use has a ratings of IAC 2 amps, VAC of 12 volts, and a total power of 24 volt amperes. Now, what is the minimum value of load resistance, Rmin, that can be used without exceeding the transformer rating? Vm would be equal to root square of 2 times VAC, that will give us 17 volts. Im max, that would give us 4 amps. Note that you are allowed to make the maximum peak to be equal twice the rated current of the transformer. Okay, why? Because you are not exceeding the specs. That's still within the specs. Okay. R minimum would be equal to a 17 over 4, that equals to 4.25 of an ohm. Okay. Now these waveforms would give us an idea of the RMS of a half sine wave or a full sine wave. Note, for a half sine wave, the RMS for such a wave would be equal to 0.5 of V peak or V max, half of it. This one is a full wave. As we all know, it equals 0.707 of V max or V peak, which is V peak over the root square of 2. And note that even though this one looks like it's double that one, but actually the RMS of it is not double that one. Okay. Why? Because the RMS in itself, it's peaky, because it's always squared. You square the function, that's why it's peaky. So therefore this one equals to 0.5 of V max, and this one is 0.707 of V max. Okay, now if you intend to measure these waveforms using a multimeter, a true RMS multimeter, you have to read that VDC first for any of these waves, okay, and square it and add it to whatever VAC is read by that true RMS meter, and also square it, add both of these values together and put them under the root square, okay, to get the true RMS of it, which will equal exactly to what we have in here. Now the percentage of transformer power utilization. How much we got back from our transformer? How much we utilized when we used it in that half-wave rectifier? We have that VL in RMS, like we said before, it would be equal to VM over 2. Half of VM, that's the RMS for it, and that would equal to 0.0707 of the VAC. We have the IL in RMS, okay, it's equals IM over 2, and that would equal exactly to the IAC, because we get the full out of it, the current that we can get out of it, okay. And the power of the load in this case would be equal to 0.707 of the VAC. So that means we got about 70% of the power of the transformer. We are able to get up to 70% of the power of the transformer in the load. Okay. So that means we paid for 30% that we are not able to use. You can get up to 70% without exceeding the specifications of the transformer. Okay, now we intend to use the storage element, which is the cap, to smooth that output voltage. When a capacitor is used as an energy storage element, the DC output voltage increases and becomes smoother. Okay. This, of course, stresses the transformer because it has to supply or store the capacitor energy in a much less time than the cycle time. This means the transformer current must be high enough to store the required energy in a short time. Okay. And that all action, it happens between this point and this point. So the transformer actually just works for a very short duration. We're going to call it the conduction duration. Okay, this is the duration from this point to this point. And the rest of the time, it's not doing anything at all. So that transformer just works for a bit of time. And that means a high peak of current will go on supply the storage cap in a very short durations. Actually, you won't see those 90 degrees corners in there. Okay, this is just to simplify our equations and to make our life easy. In here, as you see, you have the triple voltage created at this point in here. It's being amplified in here. Okay. Now the actual shape of the current that charges the cap, theoretically it should be like this, but practically it will look like this. Those corners will be smoothed due to the inductance of the circuit, or the little resistance in the wires, and the inductance of the cap itself. So you get something like this, like a very, very small sine wave. Now this shape of current will stress the transformer because it has to supply all that energy in a very short duration. That means we are not going to get much out of our transformer when we change the shape of the waveform. Now let's go to a few more equations. We have that VR, the ripple voltage. It's always in peak to peak. Whenever we refer to VR, that means it's in peak to peak. We have that IT is the transformer current. We have that T, which is the cycle time, 1 over F. We have the TC, it's the conduction time, the time where the transformer charges our cap. We have the TD, the capacitor discharging time. We have the Q, which is the charge. And the equations that we have, the VDC will always be equal to the root square of 2 of the VAC, that's the peak voltage, okay, minus VR over 2, just half of it, that would be equal to our VDC. The Q, as we always know, it equals the current multiplied by the time. the charge stored in the capacitor equals the charge stored by the capacitor, because you're going to store that energy in that cap for a short duration, and the rest of the duration the cap has to supply that charge to the load. So Q charge would be equal to Q discharge. Now putting these equations together, that's the charging part, that's its charging part. Okay. And from this equation we know what the I peak will be. That I peak, the maximum peak current that will charge the cap. Okay. And the RMS for such a waveform, that pulse that we had in there, would be equal to squaring that peak current, finding the area underneath it, okay, and after that averaging it and put it under the root square. That's the RMS of any pulse that you have, that rectangular pulse that we saw before, which be equals to I peak under the root square, the conduction time divided by the whole time, the whole T. IC would be equal, as we always know, it's equal C dV by dt, and C in this case would be equal IC dt over dV, and from here we can calculate the value of the cap. Okay, that's a standard equation, and we have that triple voltage, and to calculate it, it equals always to Vm, the maximum voltage, peak voltage, minus Vm sine 90 degrees minus Tc over T multiplied by 360 degrees. And that's in a sense is how much we are going to get out of the Vmax that we have in here. Okay. And the duration we are going to be considered as a conduction time. It's T over 4 in milliseconds. So that means about 45 degrees. It's going to be considered as a conduction duration. This is a bit of conservative design, but it does its meaning, and we get the most out of our transformer when we use such a conduction duration. The value of conduction time Tc is very important. It affects the percentage of transformer power utilization, ripple voltage VR, and capacitor value C. The designer should make a good compromise in order to come up with an acceptable transformer size, capacitor value, and meet the power supply requirements. To make the previous equations more meaningful, a conduction time duration of 2.5 milliseconds, that's a 45 degrees, is selected. That's for a 50 Hertz mains supply, by the way, which is a 20 millisecond duration for the full cycle. I peak in this case, since we selected that 2.5 millisecond, is allowed to be equals to 8 times the IDC. Okay, so have to supply 8 times that current in a very short duration into the cap, so the cap will be able to supply that energy throughout the cycle when the transformer is off. ITRMS, in this case, as we said before, that's the equation we stated before, it will equal the conduction time over the full T and the root square multiplied by IP. Since we are allowed to have 8 times that IDC, that's in magnitude, the RMS for it would be equal to 2.8 of the IDC. Okay, that's shown in here too, or explained in the same manner. This is the peak where you are allowed to have 8 times the IDC that we have, and the RMS for it, that's the equation. And in this case, the IDC max would be equal to 0.35 of the IAC. So you can't have more than 0.35 of whatever is written on that in your transformer when you use that cap. The ITRMS equals the IAC when the full current capability of the transformer is utilized. That's not the case, of course. Like we said, we got only 0.35 of it. VR, the ripple voltage in this case, as we said before, it would be equal to 0.29 of VM. That's VM minus 0.707 of VM. That will give us about 30%. And we average it to the half of it, add half of it to it. You get your VDC to be equal to 0.855. So you get 85% of your VDC. When you put your cap in there, you get up to 85% of the maximum voltage. So you got already about 0.35 in the current and 0.85, 85% of the maximum voltage. And calculating the value of the cap, that's the equation that we intend to use. It was derived previously. Okay, now let's see an example on this. Well, further analysis first, and then we see the example. Using the quantities that we calculated before, the PL max, the power of the load, the maximum power of the load, would be equal to the VDC times the IDC max. The VDC, in this case, would be equal to 1.2 of that VAC. The IDC max, like we said before, equals 0.35 of the IAC. And the BL max in this case, multiplying these numbers, would give us about 42%. So you are getting 42% out of your transformer when you put that cap. In the first case, without a cap, you got about 70% out of it. And here you are getting about 42% out of it. So you are paying for 60% of the transformer that you are not going to be using. Why this is the case? Because whenever you change the shape of the waveform you are taking out of the transformer, you are altering the RMS of it, which means that you are not gonna get all that it has to give. The idea that it was specified for a sine wave. When you alter that shape, that's what happens. From the above calculations, we found out that the PTPU dropped from 70% to about 40%, or 42%. Now to example 2. A transformer has the following ratings. That's the same transformer. Like we said, we intend to use the same transformer for the various types of linear power supplies. It has a ratings of IAC equal 2 amps, VAC 12 volts, and a total power 24 volt amperes. This transformer is to be used in a power supply which uses a half-wave rectifier and a smoothing capacitor. The conduction duration is chosen to be 2.5 milliseconds. Find the minimum load resistance R min, the power of the load PL, capacitor value, ripple voltage, VDC, and IDC max. The VBM would be equal to 17 volts. The ripple voltage would equal to 4.9 volts. The VDC would equal to about 14.5 volts. The IDC max would be equal to about 0.7 amps. Okay, that's 0.35 of the IAC. That would equal to about 0.7 amps. And the minimum resistance would be equal to 20.7 ohm. That's the minimum resistance that you have without exceeding the specification of the transformer. Now the power of the load in such a case would be equal to 10.15 watts. The capacitor size, plug in the values into the equation, would give us around 2500 microfarad. And the percentage of the transformer utilization, like we said before, plugging the numbers would get a 42%. The component ratings. The reverse voltage of the diode must exceed 2 times the maximum voltage of the secondaries, maximum peaks. The average forward current must exceed the value of the IDC. Capacitor ratings, capacitor voltage must exceed the maximum secondary voltage, Vmax. We should know that the tolerance of such a caps would be from minus 30% up to 50%. That's common in electrolytic caps. The fuse ratings. The fuse type, it must be a T and anti-surge, located of course at the primary side of the transformer. Fuse voltage ratings must be 250 volts or greater than VAC primary, whatever it is. Fuse current, a good approximation is 2.5 multiplied by the IAC multiplied the VAC, that's for the secondary side, divided by the VAC of the primary side. Okay, and I have a full equation. I have a full lecture describing the fuses for the various types of these power supplies, and I have two additional lectures on miniature fuses and their applications and all of their aspects. For the power supply of example 1 and 2, okay, that one without a cap and that one including the storage element, the cap, that would be equal to 2.5 multiplied by 2 amps multiplied by 12 volts divided by the 240, that's the supply, the main supply voltage, and that would give us a 250 milliamp fuse. And this value is high, by the way. That's because of the harmonics and the stored energy in the transformer that has to be returned to the main during that off peak, because this power supply, it limps and it reduces harmonics. Okay, so therefore you will have a high value of the fuse for this type of power supply. This type of fuse will not provide protection to the transformer nor to the load in the case of overload, and I discussed that in my 2 lectures on miniature fuses. Overloading fuse does not protect the transformer overloading. It provides protection only for short circuits or heavy overloading. So don't expect that when your current rises by about 10% or 20% of the required value, that fuse will blow. Actually, in many cases it won't. Let's see what else we have. So a few remarks in here. See what we have. Increase the rating of the diode and capacitor voltage because in most cases this does not imply an additional cost. The capacitance value for this type of power supplies is moderate because of a long duration of discharge time, but low IDC current and high ripple voltage. This power supply provides high VDC but low IDC. Transformer utilization is poor. One diode is used. The transformer does not provide the capacitor nor the load with the energy for most of the time of the cycle time. It is active only during the conduction time DC. I hope that was useful, and I'm looking forward to present more lectures on the other types of power supplies. Thank you for watching.